connections. We want to make some connections that are pretty powerful connections. We started off looking at limits and continuity, building our definition for the derivative. And when we started talking about the derivative, the big concept of the derivative was rate of change. Rate of change of position is velocity, and the absolute value of velocity is speed. So we're talking about velocity and speed here for the derivative. Then we're over here looking at the definite integral, and we're talking about area under a curve. What does this area under a curve mean? How much room do I have? How much area do I have, region I have under a curve? Those two things are connected. If somebody came and told you how much land you have in your backyard is related to how fast your car goes, you'd say, no, it's not. Maybe it is. Well, in calculus it is. And it's related, that connection is made by something called the fundamental theorem of calculus. The fundamental theorem of calculus has two parts. Part one makes that relationship. Part two tells us how to work this definite integral thing, how to find that area under the curve. So I want to look at the fundamental theorem of calculus. And as we look at the fundamental theorem of calculus, we're going to make statements about how do we apply it. So the fundamental theorem of calculus has two parts. I like to abbreviate it as the fun theorem of calculus, but my students sort of balk at that. The fundamental theorem of calculus. And it's got two parts, so I'm going to call this part one. That would be a good place to name it. Then we'll call the other part, part two. The fundamental theorem of calculus talks about functions. Now remember when we started talking about what does calculus do, I made a statement. Arithmetic basically works with numbers. Algebra takes it up a notch and works with variables. Calculus works with functions. So all the things we've been doing with calculus, we've been doing them with functions. So I want to talk about a function f. And I want to say if f is a continuous function on some closed interval ab, it's a continuous function on ab, then, now notice this is a little f. This is a little f function. Then I'm going to define a big F function, a cap f function, as follows. F of x is equal to the integral from a to x of f of t dt. Now I've got a dummy variable over here for t. But what this says is I can make a big F function out of the little f function by taking its integral. And this function has a derivative at every point in the closed interval AB. And I'm getting ready to run out of room here. So, and the derivative of the big F function. Now remember, we defined the big F as the integral of little f. Now I'm taking the derivative of big F with respect to x is equal to the derivative with respect to x of the integral from a to x of f of t dt. And that's equal to f of x. Now what does that mean? F is a continuous function on a closed interval AB. If I can find a continuous function on some arbitrary closed interval AB, then I can define a big F function as the integral from a to x of f of t dt. This has a derivative everywhere, so this is everywhere differentiable on that interval. And this is the biggie right here. This is the biggie. Drum roll. The derivative of f at x is equal to f of x. Well, what does that say? It says over here in differential calculus, I have something called the derivative. And over here on the other side in integral calculus, I have something called the integral. And that the integral and the derivative are the same thing, backwards. What we're saying is, if I have a function and I take its integral, and then I turn around and take its derivative, I'm going to end up with the same thing I started with, plus or minus a constant, maybe depending on which way I do it. If I take a function, take its derivative, well, if I do it this way, I don't have the function. If I take the derivative first, then take the integral, then I'm going to end up with plus or minus a constant difference. But what it's saying is, if I have a function, take the integral of it, and then take the derivative of it, I'm going to end up where I started from. The derivative of the integral is the integral of the derivative is what you started with. Sort of like inverse, they're not inverse functions, but they're operations that reverse each other, plus or minus a constant. So, the fundamental theorem of calculus part 1 makes a connection between the derivative, speed, velocity, and the integral, area under the curve. The second part of the fundamental theorem of calculus is sort of what I like to call the applied part. It tells me how to do something. It tells me I've got a situation here, it tells me how to find an answer. The second part of the fundamental theorem of calculus says, again, so let's call this part 2. And on part 2 of the fundamental theorem of calculus, it's going to tell me f is again a continuous, continuous on every point of AB. So if I have a little f function that is continuous on every point of a closed interval AB, and f is any antiderivative of f, of little f, on that same closed interval AB. Now look at what we got here. I've just got my hypothesis here. If little f is continuous on every point of AB, so it's continuous on that closed interval, and big F is any antiderivative. What do I mean by any antiderivative? Remember, when I take an antiderivative, I'm going to get the same thing every time, plus or minus some constant. It's going to be a constant difference. So this constant, when it says any antiderivative, what I'm saying is I can add any constant to it. Doesn't matter what constant I add to it, the constant's irrelevant. On AB, then the following happens. This is cool. The integral from a to b of f of x dx, we can compute this. We don't have to find area under the curve with Riemann sum. We don't have to go grab our calculator and use Math 9 or Second Calc. We can do it ourselves. And this is how we do it. We take big F. Now remember, big F is the antiderivative. We take big F evaluated at B. We take big F evaluated at A, and we subtract them. This part of the fundamental theorem is also known as the integral evaluation theorem. This tells us how to evaluate an integral. You take the antiderivative, any antiderivative, and you say f of b, where b is the upper limit, minus big F of a, where a is the lower limit. Now, any antiderivative, so we've got a constant problem in there, but actually we don't. We don't have a constant problem, because when I take the antiderivative here, I get a plus some c. When I take the antiderivative here, I get another same. It doesn't matter which one you use, you got to be consistent. I get the same plus c. What am I doing to these two things? I'm subtracting them, so these two c's, no matter what they are going to end up canceling out anyway. So for this any antiderivative, I don't have to worry about what that constant is, because when I subtract them, those two constants are going to cancel each other out. They're going to subtract and make 0. I want to look at a few problems.